All right, well, welcome back, everybody. Just a quick announcement. Don't forget today you have exam number 3. So give yourself plenty of time, same format as before. If you have any questions about those, uh, I'm open to any questions about those chapters. If not, I will continue with the next chapter. Excuse my voice. I think I'm coming down with something. It might sound a little different. All right. Any questions then? All right. Well, we are on chapter 10. Chapter 10 deals with chemical reaction. Okay, so now bring us up to date where we're at. We started off with the elements, learn about the properties of the elements, and then learn about elements losing or gaining electrons to form ions, positive and negative ions. We started putting these ions together to make ionic compounds. Now these compounds and the covalent compounds started learning about how to name them and so forth. We're going to use those compounds now to have them react with each other. And hence we are at the point of chemical reactions. Now there are only 6 types of chemical reactions that have all the chemistry involved. All the chemicals out there, there's only 6 types of reactions. I've introduced already one, the last chapter with acids and bases. That was one type called a neutralization reaction. We'll have more on that here in a little bit. And then another one I may have mentioned or not, but something we use every day, especially if we drive a vehicle, and that's called a combustion reaction. And that's burning of hydrocarbons. And if you did this weekend, did some cookout with a propane tank, that was a combustion reaction. You have gas in your stove, and you're burning that to cook. That's a combustion reaction. Okay, and we're going to have a lot more. Not a lot more, 4 more types of reactions, and we're going to learn how to identify them. And then on top of that, we need to learn how to balance these chemical reactions, because based on the law of conservation of matter, we need to balance these reactions, because we're not creating matter, we are just taking matter and moving it around. So if we start off with 10 carbon atoms as a reactant in some form, then we need to end up with what same number of carbon atoms as products. They'll be in different forms, but it's still carbon. Okay, and that's true for all the elements. All right, so as I stated, matter is neither created or destroyed. And so one way to look at this is as follows. If we knew the total mass of reactants and let the reaction proceed, and then we find the total mass of all the products, we will learn that the mass is the same. Okay. There was an experiment a demonstration actually that I could do while we're in face-to-face. I can't do it here, but basically, which is baking soda and vinegar and a beaker in a special flask, Erlenmeyer flask. And the way it worked, and let me demonstrate that. We will have a flask, Erlenmeyer flask, okay, with some acetic acid, aka vinegar, okay. I just say acetic acid. Okay, and then we will put a little balloon over the top, and in that balloon we will put some sodium bicarbonate, aka baking soda. Okay, and then all this would be sitting on the balance, and it would weigh, I don't know, 100 grams. And so we'll weigh it beforehand, and then we'll take that balloon and flip it over and force that sodium bicarb into the liquid of the acetic acid, which is an acid-base reaction. Sodium bicarb is the base. The acetic acid is the acid. One of the products that is created is carbon dioxide and water. The result being that after a few minutes, that balloon would inflate. Okay. And so that balloon would be up in here, inflated with carbon dioxide, and then the liquid of all the other salts down at the bottom here, unreacted vinegar. But the point being that we would continue to monitor the mass of the whole system, and it would be 100 grams total, even though you could see quite clearly that there was a reaction that was occurring. Obviously, this fluctuate a little bit because that rubber, the rubber dynamic group contact. So there's a little bit of leakage of carbon dioxide, but for doing a quick and dirty type of example, it really demonstrated the conservation of matter, and that's what we got to do. And so, like I said, if you have 100 atoms of carbon, I'm just using that as an example, in the beginning in the form of sodium bicarbonate. At the end, you need to have 100 atoms of carbon, in this case, in the form of carbon dioxide. That's essentially what conservation of matter is telling us. All right, and that's another way to put it, 254 carbon atoms, 254. When we do that, we start putting numbers in these chemical reactions. When we write them out, we put in coefficients, and those coefficients is the numbers that we utilize to balance these chemical reactions. So you can end up with, hypothetical reaction. We got A plus B reacting to give us C plus D, for example. And after we balance it, we can say, okay, we need 2 A's and it gives us 3 C's, and maybe we need 3 B's, and maybe we need 5 D's. Those are the coefficients we utilize to balance the chemical reaction. Okay. Those coefficients are important because knowing those coefficients, we're going to be able to take that to the next step of, after we balance this chemical reaction, we're going to take those coefficients and actually start doing calculations. And these calculations would be an example. Let's say we start off with 10 grams of A. Maybe we need to calculate how many grams of D we would make on this reaction. All right. And so we're looking at the relationship between A and D, which is, in this crude example, is a 2-to-5 ratio, which is important in our calculation. So we got to learn how to balance these chemical reactions. And for some of these chemical reactions, balancing, unfortunately, and they're simple. It's a trial and error. We throw a number in and see with a number that works. For some of the reactions, fortunately, the complexity of those reactions is not very complex, so we can do a straightforward, simple trial and error. Throw in a 2 here, maybe a 3 over here, and see things how balance out. There are some of the chemical reactions we're going to talk about. We have more of a systematic approach, okay? And we'll definitely go through all of them. All right, so balancing, again, basically rehash of what I just talked about. Okay, first, you could be given a chemical reaction written in words. First, we write the chemical reaction out, okay, into the formula form. If they're ionic compounds, then we first write them into ions before we put them together. So, like we've been doing, to make sure we put them together in the correct ratio. Okay. Then we start adding coefficients to make sure that atoms get balanced in the left, on the reactant side and the product side. And that is our balancing. For example, if we look at this simple reaction, we have 2 hydrogen atoms. Here's the other aspect. Remember when we talked about the physical states of the elements, okay? Well, we're going to have to refresh our memory on those. Who are solids, who are liquids, who are gases. If we're talking about an aqueous system, we got to remember the AQ as being an ionic compound that is soluble. We just talked about that using the solubility rules, okay? And so hydrogen, also remember that a lot of the elements are not a lot, 7 of them are diatomic. So the wording could be, for example, here it could be worded, the hydrogen gas in the presence of oxygen gas reacts to give you water. That could be written out. So you take that information and you convert that information into a chemical reaction. So here we have hydrogen gas, which we know is a gas. Second of all, we also know it's one of the diatomics, so we got to make sure we put it down as H subscript 2, okay? We also know that oxygen is diatomic. There's only 7 elements that are diatomic, so we can't forget that. So it would be incorrect in that comment if we were to write H plus O, okay? And to give us, reacting to give us H2O. What that would be incorrect. Okay, hydrogen does not exist by itself. Very stable. Okay, hydrogen can be react as an element by itself, but it's not very stable. It's very short lifetime. And so hydrogen, you have to realize that it is diatomic. Okay. And remember that it is, so we're going to put that 2 in there. All right, so we got hydrogen, which is diatomic. Okay. And then we have oxygen. So let me back up the reaction a little bit. So hydrogen, let's first write it as if we just converted the words into a chemical reaction. And we would write it as so, okay? H2O. All right. So you can see, I'm just going to leave out the physical states right now. You can see that if I wrote it like this, that we don't have a balanced chemical reaction. All right, if we look in the reactant side, hydrogens, we got 2 hydrogens total on the left-hand side, and we have 2 on the right-hand side. So hydrogens are balanced, okay? They're happy. Okay. Now we look at oxygen. Oxygen in the reactant side, we have 2, okay? But on the product side, in the form of water, there's only 1 oxygen. So we have to balance it. And so what we do is we can put a 2 in front of water, okay? And so what that does is increase our number of oxygens. Okay, so now we have 2 oxygens to account for the 2 oxygens in the reactant side. But what does that do? That kicks us up to 4 hydrogens. That's okay. All right. Now we go back to the reactant side and we put a 2 in front of the hydrogen. So now we have 4 hydrogens on the reactant side, 2 oxygens on the reactant side. And on the product side, we have 4 hydrogens in the form of water and 2 in the form of oxygen. The point of this just little exercise I did here is that when you're balancing, sometimes what you do is you put a number in the product side, and then that increases one element's number, so you go back to the reaction side. And sometimes you may need to go back to the product side. So you go back and forth as needed, such that that everybody is balanced. Okay. Now, in doing that, you might end up with the numbers like, okay, instead of what I got here, maybe you did 4, and you did 2, and you did 4 right here. All right. Now, if you do the count, you'll see that, yeah, they're balanced. Okay, you got 8 hydrogens on the left side and 8 on the right side. You got 4 oxygens in the left, 4 on the right. So the atoms are balanced. However, like we do in mathematics, what you want to do, if this is where you're at, last thing you check if you can, the coefficients are the lowest values possible. Okay, so you can see that every coefficient here is divisible by 2. And so that brings us to this balanced chemical equation. So if you end up with a large coefficient, no worries, get everything balanced, do what you need to do to get balanced, and then check the coefficients and see if you can bring it down to the term to use in mathematics, and bring it down to the lowest terms, okay? All right, so look how we can see there's balance here. On the left side, denoted here by the 2 hydrogens, the 2 dark spheres, those are 4 hydrogens here total. And on the right side, we have 4 hydrogens. There's 2 water molecules, And the hydrogens now are in the form of H2O, okay? Because H2O has two hydrogens for every H2O molecule. Oxygens, we have two O's on the reactant side, and guess what? We got two O's on the right side, okay? And so we have a balanced chemical reaction. Now, what we take away once we know that is we look at the ratios between, when there's no number in front, like there, it's understood like in mathematics to be a 1. So the ratio of hydrogen to oxygen is a 2-to-1, okay? Which means that we can write that ratio as follows: 2 hydrogens over 1 oxygens, or does this bring back memories? Or as 1 oxygen over 2 hydrogens, okay? That's our ratio that connects the hydrogen and the oxygen, 2-to-1, written with hydrogen in the numerator or hydrogen in the denominator. And like we did way back when we were converting units, remember it was state you write that ratio, that conversion factor is a ratio. You can write it one or two ways. Which one we use depends on the question, okay? And so if the question says, if I have 10 atoms of oxygens, how many atoms of hydrogen do I need? So I would use the coefficient, the ratio on the left side. Why? Because my oxygens will cancel, and now I've got hydrogens in my units. You know, how's that coming back? Way back when we were doing the unit thing. All right, so then if I start off with 10 oxygen atoms, I need 20 hydrogen atoms. Okay, because you can see it's a 2-to-1 ratio. All right. Now, not only are we looking at reactants, but you can look at the ratio between the reactants of hydrogen and the products, which is a 2-to-2. And so therefore we can go 2 hydrogens over 2 H2Os, or invert it, 2 H2Os over 2, what did I do? That's hold on, give me a second here. Let me fix it. My ratio is 2-to-2, 2 hydrogens over 2 waters, or I can write as 2 waters over 2 hydrogens as that ratio, okay? And the same is true for the relationship between the oxygen and water. It's a 1-to-2 relationship, so we can write the ratio as follows, okay? All right, so that balancing gives us that ratio relationship between reactants and products. So that's why it's crucial that we learn how to balance them, because that ratio is going to be important in the calculations that we're going to eventually be doing. All right, for example, we have this, which could be written as nitrogen in the presence of oxygen reacts to give us ammonia, NH3, okay? So that could be written in words, and we take those words and convert it to this chemical reaction. And we know that nitrogen and hydrogen are both diatomic, so we're going to make sure we write it in the diatomic form, okay? All right, so one way to attack this problem, these are the type of reactions that are basically going to be like a trial and error, okay? But no big deal here. We can break it down. I'm all about systematic approach, so let's break it down. We start off, okay? We start with 2 nitrogens, 2 hydrogens, okay? And then we have 1 nitrogen and 3 hydrogens. Okay. So you can see the way I wrote it that we're not balanced. Nobody's balanced. All right. So, but what other thing I can take away? Remember when we were putting the reactants together, like remember we were doing the nitride ion Remember we did the nitride ion and we were maybe putting it with calcium ion. Remember that? And I said, find a common number, common value, in that case was 6. So that meant we needed 3 of the plus 2s and 2 of the nitrides. Okay. Well, look at this here. We have a similar situation. We're going to take that common number scenario and let's take a look at the hydrogens. Okay. Now, I see I have 2 hydrogens here, but 3 over here. So what if I were to make a common number? What if I were to make a 3 hydrogen, 3 in front of hydrogen gas, and a 2 there because the common number is 6, right? And so now my first step, I still got 2 nitrogens here, and I'm just keeping track of my material here. And now I change it. Now I got 2 nitrogens and 6 hydrogens. Whoa, look at that. Everybody's balanced. I got 2 nitrogens, reactants, 2 as products, 6 hydrogens as reactants, and 6 as hydrogens. And that was done by recognizing that I got 3 hydrogens here and 2 over here. Maybe I find a common factor, common number, see how that works. And in this scenario, it worked. Okay. All right. So now our ratio is between and once we balance it, the thing we got to remember now and keep in mind is now I have this relationship between reactants, or I can invert it. Okay, and that's the relationship between reactants. But I have a relationship between hydrogen and ammonia, which is 3 hydrogen and 2 ammonias, which I can write as that, or the ratio, I can invert it. Okay. And then the other relationship is a nitrogen with the ammonia. So I got 1 nitrogen over 2 ammonia, or invert that. Okay. And so I have 2 reactants in the product. And from that, I have a total of 6 ratios that I can utilize depending on the type of question I would be asked to do any calculations, you know. And you might say, well, you know, what kind of question could I be asked? Well, let me erase here. It could be something to the order of, all right, if I have, I'm going to change the color here. If I have 10 molecules of nitrogen, how many hydrogens do I need? Okay. And so I start off with what I'm given, 10 hydrogens. I'm going to have a conversion factor. Does that bring back memories now with respect to the conversion factors in our units? I know that I want hydrogens in the denominator. Why? Because I want hydrogens, excuse me, what am I saying hydrogen? Nitrogen, excuse me. Let me erase all that. Okay. I got 10 nitrogens because that's what I'm given. Okay. I set up my conversion factor, which I want nitrogens in the denominator, right? Because I want those to cancel out. And what am I looking for unit-wise? I'm looking for hydrogen. So that's going to be the numerator. Okay. And now the ratio is the coefficient here. So it's a 3 to 1. So now if I start off with 3 nitrogens, I'm going to need 30 hydrogens for that reaction to proceed to maintain that 1 to 3 ratio. Okay. And that's how we're going to utilize this. Now we're talking about just atoms right now, but we're going to use way back when in the acid, not way back when I talked about moles. We're going to convert those to moles when we get to explain what moles are. And from moles, we're going to get to grams. Okay. This ratio, in fact, I'll give you a heads up, it's called the mole ratio. In this case, it's 1 to 3. And I can do that. You know, I use hydrogen, but I could have easily gone for, if I start off with 10 nitrogens, how many ammonias do I need? Okay, which would be 20. Okay, because then I would use the relationship between the nitrogen and ammonia, which would be this one right here. Okay. All right, here we have hydrogen in the presence of bromine. Okay. Again, it could be worded like that. Gives you hydrogen bromide. Okay. If this was an aqueous solution, it would be called hydrobromic acid. Okay. So this is hydrogen bromide because it's in gas physical state. All right. So, well, we can do a couple of things. First, let's take a tally of what we have. We got 2 hydrogens over here. I got 2 bromides over here. I only got 1 hydrogen and only 1 bromide. Okay. So what if I put a 2 right in front of HBr? Okay. What that does is it kicks up my hydrogen to 2. It kicks up my bromide to 2. And sure enough, guess what? I am balanced. All right. I am balanced. So then my ratio there would be a 1 to 1 with respect to hydrogen and bromine, 1 to 2 with respect to hydrogen and hydrogen bromide, and the same with bromine to hydrogen bromide, our ratios. Okay, little bit more of a challenge here, somewhat. We have 2 carbons. I'm jumping ahead of myself. 1 carbon, okay, 3 oxygens total, 1 in the form of carbon monoxide and 2 in the form of oxygen gas. We got 1 carbon on the product side and 2 oxygens, okay? So what if we, you know, here's a little kind of tidbit that you should keep in back in mind, that whenever you see the diatomic elements like O2 or H2Br2, when we're balancing these type of reactions, again, these are a lot of it's trial and error and they're simple reactions. Okay, when we get specific reactions, we'll have more specific steps. For these, though, we have to what might save this for last. In other words, don't put any coefficients in front of the diatomics, because you'll find by saving those for last, now after everything else is balanced, it's a real simple thing of putting a number in front of that diatomic to get everything balanced out at the end. All right, so we'll leave it alone for right now. But what if we put a 2 in front of carbon monoxide? All right. Well, by putting a 2 in front of that, what that does is that kicks up my carbon on the reactant side. And total, now I have 4 oxygens, 2 of them in the form of carbon monoxide, 2 in the form of oxygen. All right, so since I kicked up my carbon, notice I started off on the left-hand side. I can move over to the product side. What if I put a 2 in front of carbon dioxide? What does that do? Well, that kicks up my carbon, and guess what? It kicks up my oxygen. Now I got 4 oxygen. Okay. It looks like everybody is happy now. We're balanced, right? I got 2 carbon monoxide in the presence of 1 oxygen reacts to give us 2 carbon dioxide molecules. All right. So with respect to physical states, refresh your memory with solids, liquid, and gases. And of course, the aqueous state, those are ionic compounds that are soluble. And if it's an ionic compound that is classified as insoluble, we use the S for solid, okay? If it's an element, A large majority of the elements were solids. We only had 2 liquids, and then the remainder were gases, right? So go back and refresh your memory about elements, which ones were, what physical state they were at. Okay. And don't forget the diatomic ones, there's 7 of them, have no fear of ice cold beverage. Remember that little statement there to help you out with the diatomics. Okay. We know about the subscripts. We've done quite a number of examples. Subscripts tell us how many atoms in that molecule. Okay. And the coefficients tell us how many of those molecules we have. Okay. So here we have a reaction, again, written down in words. So we're going to have to take what is written in words and convert it to a chemical reaction. All right. Sodium reacts with chlorine. All right. To produce solid sodium chloride. All right. Here's some key words. Sodium reacts with. Reacts with is an indication of the plus symbol, right? So we have sodium, which we know the symbol, which is Na. We also know its physical state is solid. Okay? Reacts with chlorine, not chloride, but chlorine, which tells us it's one of those diatomic. Okay? To produce is tells us that is the arrow. To produce, you might see the word yield. Sodium reacts with chlorine to yield or to produce. And then they're telling you the physical state here. Solid sodium chloride. Well, now we're back to chloride. So that should indicate we are doing and sodium. So we have an ionic compound. So like we did before, we write this in ion form first. Okay. We know sodium's in group 1, so it will have a +1 charge. And we know the chloride is a -1. It's in group 7. Okay. So fortunately, we can put them together as a 1-to-1. So we have sodium chloride is a solid. Okay. All right. So now let's balance it. We got 1 sodium on the left, 2 Cls on the right, 1 sodium on the right, and 1 chloride on the right. Okay, so what if we put a 2 in front of sodium chloride? What that does is that kicks up my sodium and that kicks up my chlorides, which makes the chlorides good to go. And now I have an atom here all by itself, and I can easily put a 2 in front of sodium, and that kicks up my sodium on the left-hand side. So now I'm totally balanced. So by doing this, this is just my little grocery list of all the elements and keeping track of, how many of each I have, so I can look at it at a glance. You don't have to do it this way. This is just one way of keeping track of the elements and crossing out the previous number, put in the new number, and you can at a glance tell you which direction you got to go to put a coefficient to balance things out. All right, so at this state, it looks like we are balanced out. So we first write the material. Oh, I forgot to put the state of chlorine as a gas. We got sodium as a solid. Chlorine is a gas. And then sodium chloride is given to us in the form of a solid. Okay. We know, question here, we know that chlorine is diatomic. Why not sodium chloride subscript 2? Okay. Let's look at that for a second. Why wouldn't that would it be the formula for sodium chloride? What do you guys think? Okay. Well, let's break it down. If that were the formula for sodium chloride, okay, that would infer that we have 2 -2s here for each chloride. That would infer that the sodium must be a +2. Well, it can't be a +2, right? Because sodium is in the group 1A, is in that group, which means it has one valence electron. So structurally, sodium couldn't be a +2 because they would lose an electron, 2 electrons. And if they lost 2 electrons, that means pulling off an electron from the next level in, which is not going to be very energetically favored, okay? Because the next layer in is full. It's got the octet. Okay. And we balance it. Note the ratio between reactants. Here it says it takes 2 sodium atoms to react with 1 molecule of fluorine gas to give us 2 molecules of sodium chloride. Okay. Here's an interesting reaction. Okay. Aluminum reacts with bromine to produce solid aluminum bromide. So we have aluminum, and we're talking about the element, okay? So it's aluminum solid, reacts with bromine, which we know is diatomic, okay? To produce solid aluminum bromide. So we break that down, it's an ionic compound. So aluminum, we know it's a +3, and the bromides, group 7, are all -1, so that we need 3 of them. So our formula becomes aluminum Br3. Okay. All right, so that's our formula. And now we got to balance it out. All right, so we got 2 bromides here, 3 over here, a dissimilar number. Why don't we find a common number? In this case, we can use 6 again. So we need 3 Br2s and 2 aluminum bromides. That balances out the bromides. The Brs, you got 6 on each side, but it kicked up our aluminum, no problem. We put a 2 there, and we have a balanced chemical reaction. Okay. Oh yeah, in physical states, don't forget those liquids. Bromine is one of 2 liquids in the element of the elements. The other one is mercury. Okay. So note the ratio, 2 aluminums requires 3 molecules of bromine to react to give us 2 molecules of aluminum bromide. Okay. All right. And then, make note of the ratios. We got 2 aluminum per 3 bromides, or vice versa, invert it so you can use the other ratio. And then the ratio between the products and reactants, 2 aluminum to 2 aluminum bromides, 3 bromides, bromines to 2 aluminum bromides. Okay, best way to look at it is this way. I got this ratio here, change that color, okay? And then I got the ratio between the Br2 and the product, okay? And then I got the other ratio between the aluminum and the product, okay? 2 to 2, 3 to 2, so on and so forth. Each one has 2 ratios, so a total of 6 ratios that we have access to. All right. Here's another reaction. Now we've been working with ionic compounds, and we know that because the products are a metal-nonmetal combination. But if you read this, you can see here that now we're working with covalent compounds. We have phosphorus reacting with oxygen to make solid diphosphorus pentoxide. Okay, diphosphorus pentoxide, 2 nonmetal, therefore covalent compound. All right. phosphorus, this is a solid, plus oxygen, reacting with is our trigger words for the plus symbol. Oxygen, we know it's one of the diatomics, and that's a gas. To make is our keyword for the arrow, diphosphorus pentoxide. So the parent formula is phosphorus and oxide, okay? And then come back and add the prefixes, di and penta is 5. Okay, so the product is P2O5 salt. All right, now we gotta balance it. As the previous case we had that common number of 6. Can you look around and see, all right, look, we got a common number here, but it's a little bit different. We got 2 oxygens on the left-hand side. We got 5 on the right-hand side. So we can find a common number between those. If we put a 5 in front of O2 and a 2 in front of P2O5, guess what? Our oxygens have balance now. And what that did is kicked up our phosphorus to 4. No problem. We put a 4 in front of phosphorus. And we are totally balanced. So now we got 4 phosphorus on the left-hand side, 4 on the right-hand side. 10 oxygens on the left-hand side, 10 on the right-hand side, okay? So we get balanced chemical reaction. And then our physical states. And then that is our balanced chemical reaction. And note the ratio here. We get 4 phosphorus over 5 oxygen, one scenario, or invert it, 5O2 over 4 phosphorus. And here we got this relationship here, but we have the O2 to product relationship, which is a 5 to 2, and then the phosphorus to the product, which is a 4 to 2, okay? Which is the same thing as saying 2 to 1, but just keep it 4 to 2, and there's no question. So again, we balance a chemical reaction. Again, be aware of the ratio, because that mole that I talked about earlier, that is our common factor in chemical reactions. That's going to allow us to go from phosphorus to diphosphorus pentoxide in the calculations, because the two what they both have in common is that unit of mole, okay? It's analogous to saying, apple to banana. Totally different species, right? But what they have in common is they're considered a fruit. That's their common factor. And the common factor in chemical reactions with respect to the elements is the mole. So we're going to take the mass of a material, convert that to moles of that material, and from that information, based on the balanced chemical reaction, are able to convert to moles of a different material. And once we know the moles of the different material, now we can go to grams of the different material, okay? Our common factor is the moles. We're going to learn about that, but it's important that we first learn how to balance these chemical reactions, because those coefficients are allowing us to go from one material to a different material. All right, so here's a problem, which is basically a different type of reaction that we talked about, acid-base reactions. I talked to you about a combustion reaction, and here's a special reaction. It's called a double displacement reaction. We're going to have them all summarized here, but you're going to notice here that we're going to have this big, long word here, okay? And so we're going to take everything we've been working with as far as the variable oxidation states of the metals, the polyatomic ions that we've been dealing with, and we're going to put them together to write the formula, okay? And you'll see that the reactants are all soluble. And if we look them up in the solubility table, the reactants are all soluble. Notice here at the end, it says solid lead sulfate. We have something that's insoluble. And we know it's insoluble, but the talent is here. But to verify it, if you go look up in the solubility tables of lead sulfate, it turns out to be insoluble. And this is another type of reaction, and where we put in two reactants that are both soluble in water, they're both listed as soluble, and then we mix them together, and they essentially exchange partners to create new partners. And in doing so, the new partners happen to be insoluble. If there is one that's insoluble in water as defined by the solubility rules, then we have a positive reaction. Okay. If the both new reactants are both soluble, then we got no reaction. But let's break it down. And we're going to do it here. We're not going to take it home. But first thing to do is, second here, is to break everything down to ions to make sure that we put everything together proper in the right ratio, okay? And so let's do the first one. Let's read the whole thing. It says here, write then balance this aqueous reaction. Nickel 3 sulfate plus, that's our plus symbol, lead 2 nitrate produce, that's our arrow, nickel 3 nitrate and solid lead 2 sulfate, okay? So let's first write this reaction in the forms of ions so we can put them together properly. So the first one, nickel, we know that is Ni, right? A Roman numeral tells us we are dealing with +3. Sulfate, direct you to the polyatomic ion table. And that would be SO4 -2, okay? Plus lead 2, so the symbol for lead is Pb. Roman numeral 2 tells us we're working with +2. Then we're dealing with nitrate, NO3-. That is from the polyatomic ion table. Produces, which is our arrow, okay, nickel 3 nitrate, okay, same nickel we have in the beginning, but let's keep them in ionic form, and plus the nitrate, okay, and which is plus solid lead 2, same lead 2 we started off with, but now it's been partnered up with the other species, which is sulfate. Okay, and it's solid. So what I did first is write everything in ionic form. All right, so now I can put them together in the correct ratio, so I have the formula. All right, so now I have nickel sulfate. It's a 2 to +3 and a -2. So we have a dissimilar situation here. So I need 2 nickels and 3 sulfates. Okay. For lead 2 nitrate, I need 2 nitrates for that. Over here, I'm going to, for nickel 3 nitrate, I'm going to need 3 nitrates because I got a +3 from the nickel. And then for the lead sulfate, it's a simple 1-to-1 because they're both of them are +2. All right, so the formula for the first reactant is Ni2SO4 parentheses, right? 3, and it's aqueous, AQ. To verify that, you can go to the solubility table and you see that sulfate is soluble with nickel. Okay. Then we got plus lead parentheses nitrate okay, also aqueous. So both of these products, reactants, excuse me, are soluble. And if we had them in two different beakers, it'd be a nice clear solution. All right, now we react and we get nickel and 3 nitrates because nickel has a +2. And if you look that up, nitrates are soluble. So it's aqueous plus lead sulfate. And that is solid. Okay. All right. Now, this is called a double, I'll go ahead and give you the name of it, double displacement, DIS, placement, displacement reaction, shorthand RXN, is the third type of reactions that we're going to be working. And this reaction is governed by the solubility table. Solubility table. So what we just did, we took all that verbiage, all that words, and converted it into formulas. Okay, so that's the formula, but it's not balanced. We got to balance it. Now, as a general guideline in balancing double displacement reactions, my suggestion is this: follow the polyatomic ions. Balance those first follow those and get those balanced, and everything just falls in place. Okay. All right. For example, I have 3 sulfates on the left-hand side. Let me change my color here. I got 3 sulfates on the left-hand side, and I only got 1 on the right-hand side. I got 1 sulfate over here, but I got 3 over here. Okay. I got 2 nitrates over here on the left-hand side, and I got 3 nitrates on the right-hand side. Okay. So I'm not worried about the metals here. Follow the polyatomic ion tables. Now, you can do one or two things. Since I got 3 sulfates, I could put a 2 in front of a 3 in front of the lead sulfate. So that's one way to go. All right, but let's work on this 2 to 3 difference. We have a common number, right? Again, that common number in this scenario is 6. That means if I put 3 in front of lead nitrate, now I got 6 nitrates, right? And if I put a 2 in front of nickel nitrate, guess what? I got 6 nitrates. So it looks like my nitrates are good to go now, all right? Now, in doing so, my leads kicked up. I got 3 leads here. All right, no big deal. Let's put a 3 in front of lead sulfate, okay? So now I got 3 leads and 3 leads, okay? So the leads are good. The nitrates are good, okay? And in doing so, putting a 3 in front of lead sulfate, and now I got 3 sulfates right here. So now that kicks up my sulfates to 3, which balances out the sulfates I began with. So they're happy, check that off, okay? When I put a 2 in front of nickel nitrate, that automatically kicked in my, balanced my nickel. So guess what? I'm balanced. And I did this by follow the polyatomic ions. I follow those. The corresponding metals all fall in place by default. Okay. All right. I could have started with 3 in the lead nitrate to begin with, and I would have gone to the same spot. But I just tend to, like, when I see a disparity of like a 2 to 3 ratio or 1 to 5, like we did earlier, 2 to 5, something like that effect, I tend to do that first and then go on to the rest. Whichever one you want to start off with would have been fine. As long as you get to the final number. All right. So let's clear up my mess here. Let's write it down. So we have a balanced chemical equation. Now, double displacement reaction, okay? In order for this to be a positive reaction, one of the new products is insoluble in this aqueous solution. Notice both the reactants are soluble. What they've done is just exchange partners. The nickel now is combined with the nitrate, and the lead is now combined with the sulfate. Okay, those are the two new partners. And then after you just mix the partners up, check their solubility. Notice that the nickel nitrate, the nitrates are soluble, but the lead sulfate is insoluble. So this indicates we have a positive reaction because of that insoluble material. And you end up with a precipitate. Okay, positive reaction. If both of these new products were soluble, then there will be no reaction. Only when you have one that's a solid that you have a positive reaction. Okay. All right. And it seemed a little bit complicated, but anything complicated, you break it down, break it down through the atoms first, the ions, and then put them together. All right. All right. So this brings us to a description of all the 6 types of reactions that we're going to work. All right. The first type is, and they're giving you general reactions here, A and B, which are, general elements. The first type, there's some people call them synthesis reactions, but the alternative name is called combination. I think it makes more sense to call them combination because it is a combination basically of 2 different elements. We got A and B, 2 different elements that come together and form a new compound, okay? Depicted here by AB, that's a compound. Compound is made up of 2 different elements. That's called a combination reaction. A decomposition, which is basically the opposite of a combination reaction. You take a species, which is a compound, and you do something to it, and you create the respective new compounds. Most of the time, you convert them back to the elements that they were made. Okay, so a good example of the first one would be, and I won't balance them, but if you take hydrogen plus oxygen, 2 elements, you create a new compound, which is water. Okay. A good example of the decomposition reaction is you can take water and undergo electrolysis, and you can break it down again back to the elements of hydrogen and oxygen. This should be an arrow here. Okay. It's messy. Okay. All right. A combustion reaction. Now, here's the thing for Chem 130. When we deal with combustion reactions, we are going to be dealing specifically only with hydrocarbons. Hydrocarbons, and I've introduced this before, are compounds that are made up of nothing but carbon and hydrogen, hence hydrocarbons, okay? X and Y can vary, but the simplest hydrocarbon out there is 1 carbon and 4 hydrogens, which is methane gas, okay? Now, for combustion reactions, and this is something hopefully you know, for anything to burn, you need oxygen. So oxygen obviously is a reactant, okay? Because the word in the verbiage in the question could be the combustion of this hydrocarbon. They give you the formula. Why they just give you the formula for the hydrocarbon. You must know that in order for this to combust, you need oxygen. So oxygen is a reactant. And as I stated, for Chem 130, The only two products that you're going to be concerned about in a combustion of a hydrocarbon are carbon dioxide and water. That's it. Okay. And that's a big problem with combustion of hydrocarbons is we get CO2. It's out to the atmosphere and it goes up to the sky and so we can't get rid of it. So combustion reaction is a hydrocarbon, presence of oxygen to produce carbon dioxide and water. Yes, I'm aware, we're all aware that a vehicle burns hydrocarbons. It uses oxygen, but it also produces carbon monoxide. And that's because of the inefficiency of our engines. Okay, they don't combust it very well, and therefore there's partial combustion. We end up with carbon monoxide. And if you ever see, if you're driving and you see somebody's pipe, there's a little bit of liquid coming out. Now you know what's coming out is that water. Water that's condensed. Most of the time it's in vapor form and it goes out to the atmosphere. But a lot of times it does condense and you can see it. All right. Acid-base reaction. We had a whole chapter in this. Okay. An acid, Arrhenius acid, is anything that produces a proton, which is denoted by this. And Arrhenius base is any compound that in solution produces a hydroxide. Now, the acid and the base always react to form water. And then what's left is the corresponding salt. Okay. So you could be given the acid and the base, and then it's understood that you know what the products are: water and the corresponding salt. Excuse me. Okay, so these are two examples of reactions that you should know what your products are and what your reactants are. Combustion reaction, always going to know, you'll be given the hydrocarbon, but you're going to be having to know that, yeah, I need oxygen, right? Plus, you know that oxygen is diatomic, so it's O2, not just O. And the only products for a combustion reaction would be carbon dioxide and water. How we balance those, we have a systematic approach, and when we get to those, we'll talk about how to balance the combustion reaction. For a combination decomposition reaction, that is like more like we've been just doing a trial and error type of scenario. Combustion reaction, we have a step-wise. Acid-base reaction, follow the protons and the hydroxide. Balance them out. Okay, the rest just falls into place. Okay, and finally, not finally, almost, we have what's called a single replacement reaction. All right, let's break it down. We have a metal, denoted here by M, and then we have a ionic compound, which is made up of a metal and X, which is some anion. What's going to happen is the metals replace each other, okay? So we have a metal in elemental form, which has a zero charge. It's an element, okay? It's going to displace the metal that is combined with X to form the new ionic compound. And then that metal that was combined with X now is converted back to the element. Classic example of this would be plating. I don't know if you have jewelry that's plated. You can plate things with gold, you can plate things with copper or silver, chrome, and so forth. And that's what's happening is what you want plated first starts off in ionic form and then gets converted to elemental form, okay? Now, how this functions, how are we going to determine this is as follows. Good old periodic table, right? All right. So if you go to the periodic table and right above the solubility rules, we have what are called the activity series. And it's a listing of metal. And if you see here, lithium is listed first, which tells you that lithium is a lot more reactive than potassium, a lot more reactive than bromide, and so on and so forth. If you look at that list, you'll see the most unreactive metal is gold, which is true. Gold is called the noble metal. This is very unreactive. It can react, but it takes very aggressive conditions to get it to react. All right. And we're going to be using a series of questions when we look at the two metals involved in this reaction. And from the answer of those questions, which is based on the activity series, we will determine whether that reaction proceeds or not. Okay. And if in this scenario, we have a positive reaction because that M went from elemental form to ionic form. And the A went from ionic form back to elemental form. Okay. So we use the activity series to answer those questions. And then finally, we have the double displacement, which is analogous to what we just, not analogous, it is what we just did with the nickel and the lead example, okay, where we have two compounds, two different metals, M1, M2. That's what the 1 and 2 represent, two different metals. It's not saying subscript. Two different metals, two different anions, okay? They exchange partners. So now where we had MX, now we have M1Y and then M2X. They've exchanged partners. Now, here we utilize the solubility rules to determine whether we have a positive reaction. And if one of the new products is insoluble based on the solubility rules, then we have a reaction. If both of the products are insoluble, let me state that again. If one of the products is insoluble, occasionally you might have both of them insoluble, but that's rare. You're always going to have one that's soluble. If one of the products is insoluble, you have a positive reaction. If both of the new products are soluble, we have no reaction, okay? So that takes us to the solubility rules. So be familiar, we went over those, the solubility rules, so be familiar with that, those rules, okay? All right, so these are the types of reactions that we're going to be working with and breaking them down and going through, okay? Combination reaction, decomposition reaction, combustion, acid base, single replacement, double displacement. Okay, so let's do some examples. In this one, we have phosphorus in the presence of oxygen. You might think, oh, I got a combustion reaction. Well, not quite. Because here, for Chem 130, when we deal with combustion reactions, we're only going to deal with hydrocarbons, okay? He is not a hydrocarbon, he is just phosphorus. So phosphorus in the presence of oxygen gives us diphosphorus tetroxide, okay? And we're asked to balance it, okay? So in here, like we've been doing before, we can do it. We're going to do a little trial in there. Here we got one phosphorus all by itself. Leave the phosphorus, the element, all by itself. Save that for last. Now, always we can, that's going to come in handy. Okay, so if I put a 2, we got 2 oxygens on the left, 4 on the right, so I can do a simple 2 in front of O2, right? And that gives me 4 oxygens. But I still got 2 phosphorus. So what if I put a 2 in phosphorus? And sure enough, everything's balanced there. Okay. All right. So that is 2 phosphorus requires 2 oxygen molecules to give me diphosphorus, 1 molecule of diphosphorus tetraoxide. Okay. That is again an example of a combination reaction. We have 2 elements that combine to produce a compound. Okay, so hopefully you can recognize that, because you could be given a general reaction like this and ask, what type of reaction is that? Okay, so recognize that I got two elements, and that produces a compound. Here we have a decomposition reaction. Okay. Now in this example here, we have iron 3 oxide, aka rust. All right. So we have a compound, and it undergoes a reaction to actually produce the elements, iron and oxygen. So you can see, as the previous case where you have the combination of two elements coming together, here we have a compound being treated, breaking it apart and sending it back to elemental form. Okay, let's balance it. All right, well, again, we have the element all by itself. Let's leave him for last. Okay, we have a dissimilar situation. We got 3 oxygens here on the left, 2 on the right. Okay, well, let's make those balance the oxygen. So if we put a 2 in front of iron 3 oxide, that kicks up our oxygen to 6. So that means we put a 3 in front of O2. Our oxygens are good, but in doing so, now we have 4 irons, so no problem. That's why we leave this element all by himself. We simply put a 4 there, and sure enough, it looks like we are balanced. Double check. I got 4 irons over here. I got 4 irons on the right side. I got 6 O's on the left and 6 O's on the right. I am balanced. Okay. Yeah, and note the ratios. Okay, the ratios 2 to 4 for iron 3 oxide 2 iron, and 2 to 3 for iron 3 oxide 2 oxygen. Decomposition reaction. Okay, combustion reaction. So write the combustion reaction for propane gas. Now, they're giving you the formula. You may not know the structure, that's okay, but they give you the general formula for propane gas. You note that we have nothing but carbon and hydrogen, okay? And so that is what is burning, propane, same propane that's the propane you utilize when you are barbecuing out there, right? So we take CH3H, which is a gas, propane, okay? And it's a combustion reaction, so what do we need? We need oxygen, right? And the only 2 products that we get, we're going to finish this one and we're going to stop here, is carbon dioxide and water. Those are the only 2 products. So what do you know? You're given the propane, or you're given the hydrocarbon, the form of hydrocarbon. You know it's a combustion reaction, so you're going to put oxygen in the reactant site as O2. Don't put oxygen by itself, because we know oxygen is diatomic. And the only 2 products that you're going to make for Chem 130 is carbon dioxide and water. Okay. Now, to balance these, this is the one we have a step with. Step number 1, balance the carbons first. Okay. So we got 3 carbons here. We simply put a 3 on the right-hand side. Okay. Number 2, balance the hydrogens next. Okay. We have 8 hydrogens over here in the form of propane. We only have 2 in the form of water. Okay. So all we got to do is put a 4 in front of water. And now we got 8 hydrogens on both sides. We got 3 carbons on both sides. So finally, you balance the oxygen. Okay, so you have a total of 6 hydrogens coming from carbon dioxide and 4 from water. So that's a total of 10 oxygens, 6 from carbon dioxide, 4 from water. So needing 10, guess what? Since oxygen is diatomic, just take that 10, divide by 2, put a 5. All right. So put in a 5 in front of oxygen, lo and behold, boom, you're done. Okay, so 4 combustion reactions. Once you write it out, you write the hydrocarbon plus oxygen to give you carbon dioxide and water. Don't forget oxygen is diatomic. To balance it, balance the carbon first, followed by the hydrogen, followed by the oxygen. Okay. All right. Well, let us stop it here. And we'll hear back in 14. All right.